In our previous guided practice, we used various information about the total vapor pressure of a mixture at 35 Celsius and the vapor pressures of those liquids pure to solve what the mole fraction of a mixture was. Let's continue this problem. What's the vapor pressure going to be if we raise the temp to 50 degrees? Using the info on the screen from the last problem, find me that vapor pressure at 50 degrees, the vapor pressure total. Go ahead and give that a try and then come on back. All right, if you're back, well, same idea. If I want the total vapor pressure, then I need the pressure that is from water, and I need the pressure that is from the ethanol. In this case, I can't use the equations we used before exactly because the pressure of water, well, indeed is going to be the pure pressure of water times the mole fraction of water, which we now know is 0.6. The problem is our pure vapor pressure of water is not 42.2 anymore. We've changed the temp. It's no longer 35 Celsius, it's 50 Celsius. So in order to get our actual vapor pressure of water, well, I already know the mole fraction, I need what the pure vapor pressure would be. Well, we can solve that. Remember that the ln of P2 over P1 is equal to negative delta H of vaporization over R times the inverse of the temp 2 minus the temp 1. Well, we know the pure vapor pressure at 35 Celsius. There's no reason we can't solve out what the new pure vapor pressure would be at 50 Celsius. And so we can find what the pure vapor pressure would be at the higher temp, and then use our mole fraction from our last problem to find out what the actual vapor pressure of water is at the higher temp. And so to do that, we need to plug in our values. Hey, the natural log of the pressure 2 minus the natural log of pressure 1, which was 42.2 torr. All that's going to equal negative. Well, delta H of water was given to us as 40,700 joules per mole. R value 8.314 joules per mole Kelvin. And our temps. Well, temp 2 is going to be the temperature we're heading for, which is 50 Celsius. That's the pressure we're trying to solve for at 50 Celsius. So 323 Kelvin minus the temperature at pressure 1. Well, that was 35 degrees Celsius, 273 plus 35, 308 Kelvin. So because we knew that vapor pressure when it was pure at 35 degrees Celsius, we can now solve the vapor pressure at 50 degrees for water. Plug these in, the natural log of pressure 2 here for our water minus 3.74242 is going to equal 0.738112. Let's add that 3.74 to both sides. The natural log of pressure 2 is going to be equal to 4.4805. Does that make sense? Well, yeah. At pressure 1, our natural log for 42 was 3.7. We're expecting our pressure to go up at higher temp, so I need a bigger number for my natural log to be equal to. That's going to give me a higher pressure when I take E to both sides. Pressure 2 for water should have been 88.28 torr. And so we know the pressure water should have been. So up here to our pressure total, I now have that there should have been 88.28 torr for the water, but it's 0.6 for its mole fraction. I then need to factor that in for 0.4 for the mole fraction of the ethanol, but I need that pressure too for the ethanol. So I need to repeat this for the ethanol. Again, there's going to be a natural log of pressure 2 minus natural log of pressure 1. Well, for ethanol, that was 115 torr at 35 degrees Celsius. So natural log of 115, that's all going to equal negative delta H of vaporization for the ethanol, which was provided to us as 38.6 kilojoules per mole. So negative 38,600 joules per mole over R, 8.314 joules per mole Kelvin, and the distribution in temperatures. 1 over, it's the same temps, we're bringing it up to 50, we started at 35, so 323 Kelvin minus 1 over 308 Kelvin. Natural log of pressure 2 for the ethanol minus 4.74493 must equal 0.7000. You notice this is a little bit smaller than it was for the water, while our delta H was a little bit smaller. All the other values were the same, so far this seems in line. We would expect the right side to be a little smaller this time for ethanol. We're going to add the 4.74493 to both sides. Natural log of pressure 2 is going to equal 5.44496. Now you notice that this is larger than it was for the water, but that makes sense. Our ethanol boils more easily. So once we're down to just looking at the vapor pressure at the same temp, our ethanol should give us a higher pure vapor pressure than water, which we'll see when we take E to both sides. Pressure 2 for the ethanol, the pure pressure at the higher temperature, comes out at 231.5 torr, which is indeed more than the water, which we would expect. The boiling temperature for ethanol is lower than water, so it should have a higher vapor pressure earlier. We can plug that in, 231.5 torr. Now when we then calculate out our pressure total, 88.28 times 0.6 plus 231.5 times 0.4. 145.6 torr. What we find is it's about double the original. I went up 15 more degrees and I got some more vapor pressure because both materials were pushing more of their liquid into the gas phase. The increase for ethanol was substantially greater than the increase for water because we're closer to the boiling point of ethanol. It's an exponential rise. But we're able to solve out what each individual gas's vapor pressure is, and then use that to combine them to solve the total vapor pressure. This is why it's dangerous to heat sealed bottles. As the temperature goes up, they start putting more and more of their liquid into the gas phase, increasing the pressure, and eventually that bottle can't take it anymore. And so while some things like canning are designed to allow gases to escape before resealing as they cool, fully sealed containers, heating them up is very dangerous. They can eventually explode because of this ever-increasing vapor pressure total inside.